Good day and welcome, everyone. This is the Introduction to Vibration Isolation for HVAC Equipment and Systems, hosted by VISMA, the Vibration Isolation and Seismic Control Manufacturers Association. Today will be presented by Angela Waters and John Giuliano. John is the president of the VMC Group, a manufacturing and engineering firm in the seismic restraint and vibration control industry. He has been with the VMC Group for over 22 years and is a PE in multiple states. He has authored many articles for both VISMA and ASHRAE. Angela is a structural engineer registered as a PE in Ohio, New York, and Washington, D.C. She has her national record through NCEES and is a model law engineer. She has worked for kinetic noise control for almost 10 years and has worked in the building construction industry for 20 years. Our presenters will do their best to handle questions throughout their presentation as the questions relate to the topic at hand. To ask a question, there is a question mark symbol within your webinar control panel. Simply click on the link to notify us that you have a question and then type in your question in the field provided. I'll now turn the floor over to John to get us started.
Okay, thank you. Thank you, Jody. Hello, everyone. Welcome to the Introduction to Vibration Isolation. This is a basic introduction to vibration isolation. We're not getting into too much of the theory. It's not going to solve all of your problems. It's rather going to help you understand a little of the terminology, let you know what to look for when you have vibration problems, just to make you sound a little more intelligent when you ask questions to really dig in. We'll try to keep it basic. We'll try to keep it simple. And if you have questions, as Jody mentioned, please type them in. They're relative to the page we're on. We'll try to get to them. Otherwise, we'll hold them all to the end. First, as the basics, most mechanical equipment contains rotating internal components. And you're familiar with them, I'm sure. Motors, compressors, pumps, basically anything that has an RPM or has cycles, it's going to be vibrating. It's going to create some sort of vibration energy that can get into the building through the floors and the ceiling. Also, it will create noise. And in general, you'll know the equipment might have fan blades, and the fan blades in particular make noise, but they're driven by the motor. So if we isolate the motor, you prevent that energy from going into the building. The compressors will also move liquid, and the pumps will move liquid through the building. Those also become vibration issues. Now, sometimes on this equipment, the vibration of the equipment itself can sometimes be damaging to the equipment. So you're not only isolating the vibrations from coming into the building, you're isolating the equipment to prevent it from damaging itself. And as you know, most of this equipment, if you're familiar with the industry, compressors especially, the manufacturer will put some kind of little, maybe cheap rubber grommet underneath their compressor to try to prevent some vibrations, but that's not going to solve your problems from coming into the building. Now, aside from the equipment itself creating some vibrations, the distribution systems for this equipment, since we're working in HVAC, we know we're moving air and water through ducting and pipe work. That movement of the air and water through the distribution system will create its own problems. When the pipe or the ductwork is going through a floor penetration, it creates vibration into the building structure. And when the equipment is rigidly attached to the piping and ductwork, the vibration from the equipment itself will be transferred through the ductwork and the pipe and then into the building that way. You'll typically, mostly though, it will be in the ceiling suspended equipment and the and rigid mounted equipment to the base, but also the humming noise that you would get. Sometimes the vibration you won't feel the vibration, but you'll hear a sound, and that sound will be coming from vibrations where the equipment distribution system is rigidly touching some building structure. Now, again, we're keeping this very basic. Placing an isolator between the disturbance, which is the rotating equipment, and the structure reduces the transmission into the structure. But it just reduces, and no vibration isolation system can eliminate the transference of the energy into the building or the noise. You can never get 100% isolation. You'll always have some residual, but generally the specifications are written and it's such where you just want to get it to where it's imperceptible to humans and it's not creating any issues within the building. But you will never get 100% efficiency. Now, an isolator, effectively any medium that deflects under load is technically an isolator. All we need is just a little bit of a deflection of some medium that goes between, and it's, as I said, it can, in the slide you can see even a soft block of wood. As long as the wood deflects and can maintain its deflection and support the equipment, it'll do something. It won't do much. You won't get much efficiency out of it, but it will technically be considered an isolator. Though the rotating equipment we typically deal with in HVAC and power generation, you'll hear discussions about inches of deflection and static deflection. And typically for it to be effective, we're looking roughly between 0.2 inches and 5 inches of static deflection. Later on, Angela will get into a little bit of some of these definitions as to what I'm throwing out right now, but right now we're talking static deflection of the medium that you're using as an isolator with the static load of the equipment on top of it. Here's just a very simple illustration of what I'm talking about with static deflection. I have any medium, I'm calling it a medium just to be generic. It can be an elastomer, it can be a spring, it could be a block of wood, it can be an airbag. But it's just a medium that's placed under the equipment. It has a free height, static height, 1 inch, 2 inch, 3 inches, whatever it may be. You place a piece of equipment, you place a load on top of it, and it's going to deflect. If it doesn't deflect and it's rigid, you don't have isolation. You need deflection. So the difference between the two heights, the free height without any load and the height with the load, is considered the static deflection. And when I talked about 0.2 to 5 inches, that's what we're measuring. So obviously, if it's just a pad or a block of wood, you'll get hardly anything. If you've got a very tall spring, the spring can deflect on the order of magnitude 4 or 5 inches, and you have a lot of deflection in your system. And it's the amount of that deflection which is critical to getting the isolation efficiency you'll be calculating later on through Angela. Now, just by deflecting itself doesn't necessarily make it an isolator. The medium that you're using, after you remove the load, needs the ability to come back to its free height. If after loading it, you remove the equipment and it stays where it was, it now doesn't have any static deflection. So the medium, it can't just be anything that squishes and stays. There are some materials that as you push on it, it would stay and not come back. That's not what would be considered an isolator. Now here's a very generic picture of a pump and some blocks thrown in there. They can be elastomers, they can be blocks of wood, but as long as they deflect it a little bit, I'll get some isolation. But it's the RPM of the equipment relative to that static deflection, which is going to let me calculate my isolation efficiency. Now, in general, the deflection of the ice, as the deflection increases, the efficiency increases at the same RPM. And that gets a little confusing because what's happening is your required deflection becomes inversely proportional to your RPM. So as I have a piece of equipment with higher RPMs, I need less static deflection to get the same efficiency. And it may be counterintuitive at first, but I have a little chart there, you see if I'm shooting for 90% efficiency, if in this specification I need to get 90% efficiency, I need the RPM of the equipment. That's one of the most important numbers you have to start with. If the motor is running at 1800 RPMs, I'm only going to need 0.12 inches, roughly 1/8 of an inch. Not much, a block of rubber, a pad or something will give me that. But as I decrease my RPMs, if I get down to 300 RPMs, you see I need 4 inches of deflection just to get the same 90% efficiency. And a lot of the newer equipment out there, due to energy efficiency standards and such, will have variable speeds built in. So when you're asking for the RPMs, you may be receiving the highest. You always have to verify that there's no variable speed drives that will bring the motor speed down. Obviously, cooling towers are the big issue with these, if anyone's familiar with those. They have variable speeds down to the order of magnitude of 300 RPMs, and they may have been designed a little faster, and you'll have a system that may only have 1 inch deflection, and your efficiency drops dramatically. And if you have the wrong deflection, and as they're switching the RPMs, it's very likely you can amplify the vibrations coming into the building. And you'll have what's called resonance. I'm sure most people are familiar with it. Angela, later on in her presentation, will talk about resonance. Now, as references, ASHRAE Chapter 48 is probably one of the most comprehensive. I'm sure many of you on the phone are familiar with ASHRAE. They have a technical committee, TC 2.6, which writes this chapter. The members of that committee have years of practical experience that went into these numbers. I stress practical because a lot of this information, a lot of the numbers out there you may see, purely analytically, you would see different numbers, but analytically doesn't take into account the stiffness of the building, the stiffness of the support structure. And as you go up higher in the building, this ASHRAE Chapter 48 will tell you need more deflection because the building itself, as you get very tall, becomes a spring. And a lot of this equipment is also attached to diaphragms or slabs within the building as you go up in the building. If you're in a building with, say, 20-foot column spacing, the diaphragm itself will be a lot stiffer than if I had a 40-foot column spacing. At some point, this diaphragm, the concrete slab that the equipment is resting on, it can become like a trampoline. So that has to be factored into the equation, which analytically most of the textbooks would ignore. Now, I'm going to go back one slide because a question did come through on RPM, just to make sure people understand. The RPM is the frequency. The question is RPM referring to the frequency that the machine is making? The RPM is the speed that the motor or disturbing element in the system is spinning, and it's revolutions per minute. So I guess I got to remember this may be international and people all over the world. So yes, we refer to RPMs rather than frequencies. And that's actually a good question I was going to touch on later, but it's important now, I guess. In ASHRAE 48, Chapter 48, and generally in our industry that VISCMA deals with, we discuss inches of deflection in RPM. We do not get into hertz or cycles per second as what would be done analytically. Using RPM and inches of deflection, or it's equivalent analytically if you went into hertz, but it's not necessary since this is the information most people will get from a manufacturer, the RPM of the motor, from the manufacturer of the vibration isolators such as Kinetics and VMC will give you the inches of deflection of our springs. So ASHRAE Chapter 48 relates those two rather than going into frequencies in hertz and cycles per second. So we've kind of, I don't want to say dumbed it down, but it's industry vernacular that we use that makes it a little simpler to compare two systems side by side rather than worrying about the natural frequency of the system. What's the RPM? What's the inches of deflection on the springs underneath, and they get you roughly the same efficiency. Well, thank you for that question. Now let me get back to where I was. Now, if you see on this chart, let me go, went back one too far. If you see on this chart, all the deflections will say up to a certain inches. So cooling towers, strain springs up to 3.5 inches. The up to is very important since, one, it is somewhat related to the RPMs, but like I was saying with the diaphragms, it's also related to the stiffness of the support structure underneath. And with rooftop cooling towers, it's extremely important that the framing underneath, whether it's called a dunnage frame or grillage frame, the stiffness of that is very important because these cooling towers get large and heavy, and the spans of these beams get relatively large. So if you're doing the analysis with an improper support structure, picking the 3.5-inch deflection might not even work for you. The stiffness of that support structure is very similar to looking at the stiffness of the building slab. If the building slab is a spring itself, you have a double mass system. And then it goes well beyond the basics outside of the scope of this particular course. Let me move on to the next. Well, I have another question came through. I guess it is relevant to this. In the case of belt drive fans, are you looking at the RPM of the motor or the RPM of the fan? It's the RPM of the fan that would be the driver, as if you're putting reducers in there, different wheel diameters. All right, now from the basics, on the basic isolator types, as I said earlier on, it could really be any medium, but in general, what we deal with for mechanical equipment, it's going to be springs or rubber pads. Right now, I'm just showing 4 examples that have springs on them, but it's more to show the attachment and function. A basic open spring isolator, it will be for a non-seismic, non-wind type of installation where you don't have any tip over concern. The spring itself would need to be stable, and there's a height over diameter ratio for stability. Again, a little bit outside the scope here, but the spring isolation vendor would rarely ever sell you a spring that's going to be unstable when it's installed. Some of them, this one shown in the picture, come with a base plate. You can anchor it down to building structure. Not designed for shear, it's just designed so it doesn't walk on you over time. The next one on the upper right, it's restrained. It's also a category of housed spring isolators. The welded design and the restrained, they're typically for wind and seismic outdoor applications when they're galvanized instead of painted. What they offer is spacing. It's hard to see in the image, but it's spacing for concrete anchorage when you're going into concrete. So for tip over, your anchors aren't spaced too closely. You can get some rating out of it. Some of them are designed for blocking during shipping. So the installed height of the equipment is the same as the free height as it's vibrating. And the upper plate on that one moves independent of the lower housing. So the lower housing stays anchored to the building. The upper plate, which is attached to the equipment, will float and move up and down with the equipment. Now, I might have passed, I'm going to go back just a slight thought on the spring isolators. When we talk about deflection, I don't want to confuse people with this. A 4-inch deflection spring that deflects 4 inches statically does not move up and down 4 inches during operation. I've had some people ask that question, and it may sound to someone in the industry that you know, a little ludicrous, but when you're not familiar with it, it's a good question. In general, after the static deflection is put in, whether it's 1/4 of an inch or 4 inches, now as the equipment is operating and it's moving, the spring or whatever vibration isolator in between would move very little. We're talking on the order of magnitude, like 1/16 of an inch, you'll see it oscillate up and down. That is independent of the static deflection. So when we're talking static deflection, we're not talking full movement. So when you look at that restrained isolator, the space between the upper plate and the lower housing is roughly only 3/8 of an inch. Even if I had a 4-inch deflection isolator in there, that's still enough so that I'll never have contact during operation between the top and the bottom. All right. Next on the lower left is a rooftop isolation curb. Now curbs are for rooftop, typically air handling equipment. Since the air handling equipment has to move air through holes in the building would require some kind of flashable system to prevent water and air leakage into the building. Those would typically have internal vibration isolation, as you can see, such that after it's roofed in, the upper portion of the curb would vibrate move independently than the lower portion, which is anchored to the building. And those would typically be wind and seismic. You see a lot of the sheet metal ones that come with the equipment. They do not come with isolation. So if you require isolation, you need something other than the sheet metal that comes with the equipment. Now in the lower right, that's a concrete inertia base with open springs. I had mentioned earlier with pumps, Chapter 48, you see here, pumps are on steel or inertia bases, and same with fans. When we talk about inertia bases, we're talking about a component that has the ability to add mass into it, and we add that mass with concrete. The concrete is installed in the field, so what would ship out to the customer, to the field, to the installer, is a concrete form, such that with rebar in it. They fill it with concrete in the field. After it cures, they can attach the pump or the fan to it before they lift it. It helps with the rocking motion, but most of the benefits of doing the analysis of an inertia base is outside of the basics, but you'll see many pumps in the basement of buildings on these inertia blocks. And they can be offered with either of the two spring types on top, an open spring or a restrained house spring, for the same reasons. What I'll do now is I'm going to transfer it over to Angela Waters, where she'll get into a little more of the theory and the math, and she'll take it from there.
Thank you, John. Okay, I'm going to talk about the theory, the terms and definitions. John has touched on these a little bit as he's been going through the basics and introduction to vibration this afternoon. So, vibration, it's basically undesired motion, and it's transmitted to the building structure and the occupants. My background, I'm a structural engineer by education and training. Just as a load in a building has a load path, vertical and horizontal, noise through a building has a noise path. And when you're talking about vibration, vibration causes structure-borne noise. So you're basically taking a vibration that's an undesired motion and you're transmitting it to the building structure. You're causing the building structure to vibrate and to create a noise path. So the isolation, how we counteract this vibration, mitigate it, minimize it, not eliminate it, as John mentioned, is we separate the source from the receiver. The source, an example would be a cyclic running fans, and the receiver would be the floor structure or the roof structure. So we want to separate those with isolation. And again, that isolation in our industry is often a spring isolator. It can be an elastomeric material such as neoprene or natural rubber. And, as John mentioned, if you take it to the far extreme, if you get, wood to deflect a little bit, then yes, you're providing a tiny bit of isolation. So when we talk in terms of frequency, this F sub D is the equipment's disturbing, or you'll hear people call it driving, the equipment's disturbing or driving frequency. And the F sub N is the natural frequency of the material, the substructure, and that formula is 1/2 pi in the denominator. times the square root of gravity times your spring constant in the numerator over the weight in the denominator. And we'll see later that you can have that in different terms of the variables. So when we talk about deflection, and John was talking about earlier how in our industry we talk about revolutions per minute or inches of deflection. When we talk about deflection, you can have vertical or horizontal deflection. But again, it's that translation, it's that movement that's deflecting. And typically when we're talking about equipment, usually it's a vertical deflection. If we get into concerns regarding wind and seismic on that equipment, then we have to consider horizontal translation or deflection. So the next two concepts are basic, but then they start to build kind of like building blocks when you're learning new concepts. And later on, I have some slides that visually show this, and I might try to advance to those slides so that you can have a visual aid here. But you have a single degree of freedom system. There's only one object that is significantly moving in the system. If you could picture a slab on grade, a concrete slab on soil that's perhaps outside an office building or a hospital doctor's office building, and you have a pump or a piece of equipment for air conditioning that's bearing on that slab on grade. The fans and motors inside are moving, and you probably have some internal isolation within that piece of equipment, but preferably the slab on grade is not moving. So the only thing that has the moving parts is your equipment. Your slab on grade is stationary. So that example would be a single degree of freedom system. Now, when you have a multiple degree of freedom system, there is more than one object that is significantly moving in the system. So an example of this, we'll see on the next slide, but this example is a 2 degree of freedom system, which is very common. 2 degrees, 2 masses of equipment are moving. So in this example, you have an internal fan of equipment moving. The springs of the isolated equipment were both moving. So if you can think back to that nice illustration that John had up with the 4 different types of spring isolator restraints, if you had a curb down in that bottom lower left hand that had springs in it, that curb would be deflecting as well as your equipment is also moving. So this really becomes a reason why internal and external isolation is either to be avoided or considered only when absolutely required. And much care has to be taken in the selection of the isolation systems when you have a 2 degree of freedom system. So typically on that slide with the nice 4 spring isolators as visual aids, in that bottom left corner with the sheet metal curb, or in the bottom right corner with the concrete inertia base with the springs, equipment that would be bearing on that would not have internal isolation. So the only thing that would be moving in the equipment would be the cyclic behavior of the fans and motors, but then you would also have the springs and the isolation sheet metal curb or the inertia base that would be moving. So again, 2 degrees of freedom. So stiffness here, and John touched on this a little bit as he was describing different building elevations and different building bays as far as column spacing. But you have relative stiffness of the material versus the structure. So the term flexible diaphragm covers usually new construction. If you go into an open, a big box store and you look up, you see the open web steel joist and the form deck, or the corrugated deck people call it. But you'll see it. It's in retail and office, and it's form deck over open web steel joist typically. And you see it a lot in retail and office buildings. Now, oftentimes for the really tall buildings that you get into, or older construction, or buildings that need a larger safety factor, such as parking garages, they're going to have what I kind of tend to think of as parking garage style structure, where they have the reinforced concrete. You're talking about columns, you're talking about large, deep reinforced concrete girders and beams and slabs, depending on, what that was selected for. But it's going to be a much stiffer structure, and it's really going to be rigid. So that is a rigid diaphragm. Okay, so now we're going to talk about damping. And we normally talk about damping in terms of a ratio. And damping is a attribute that all materials have. It's an intrinsic attribute that they have. Office buildings 30, 40 years ago experienced a lot less vibration than they sometimes do today, and that was because those buildings were filled with all kinds of materials that provided damping just by the nature of their material. Filing cabinets full of paper documents would have provided extra damping. Additional partition walls, when you had, true offices and less open cubicle space, would provide additional damping. So as our construction industry evolves, how we use office and workspace evolves, now vibration oftentimes is a much more significant consideration in office buildings because we don't have as much of this damping. Carpet provides damping. But as I mentioned briefly, we talk about in terms of a damping ratio. So looking at the damping compared to the critical damping here, this second equation here, this epsilon equals C in the numerator over the critical damping in the denominator. And the critical damping in this denominator is equal to 2 times the square root of your spring constant times your mass, or you can rearrange that in terms of weight and gravity, and you have 2 times the square root of the spring rate times your weight over your gravity in your denominator. And again, the damping factor is due to the damper, the dash pot, and the C sub C is the critical damping of the system. You can provide measured or calculated damping through Coulomb dampers, which allow for some control over the variable damping ratio. Again, it's often expressed in a percentage of this critical damping ratio. So a chart here, which will kind of help to illustrate some of what I've been trying to start to describe here with damping. But you see this red line where our damping ratio is 1, and that is at your critical damping. And the royal blue line where you have just a large wave here, amplitude, that damping ratio is 0, and you obviously do not have any damping, and that is obviously considered underdamped. This green line, which also has quite a bit of an amplitude wave here, is also considered underdamped. And really your cyan or turquoise line here, we would consider that overdamped. You're not going to get an additional advantage as far as isolation efficiency when you're over that damping ratio of 1. In this example, that turquoise line is 1.5 damping ratio. So again, as I mentioned, those that were at 0 and 0.5 were underdamped systems. And that system at 1 is, ideally what your goal is to shoot for the critical damping ratio of 1. And obviously where it was over 1.5, it's an overdamped system, and you're not getting much advantage for having, that additional damping. You're not going to see it in the isolation efficiency. So I mentioned earlier a single degree of freedom system. I painted the illustration of having equipment on a slab, outside a hospital building. And that slab ideally is not moving. It is bearing on the soil and it's just the equipment that is moving. So you just have a single degree of freedom system with damping here in this illustration. And so on the right is your spring constant, your K, and here is your damper through a dash pot or a Coulomb damper that's providing some damping to your mass here that is moving. So that would be a single degree of freedom system. Transmissibility here. Okay, it is the ratio of the displacement of the building to the displacement of the mass. In our example, the equipment is also the ratio of the force exerted on the building structure to the driving force. The value that engineers and consultants use to evaluate the dynamic force acting on the building structure or the degree of force attenuation present in the system. So that's kind of a term that if you're not familiar with it, can seem a little bit overwhelming or a little bit abstract at first, but hopefully we'll show with some charts here and some equations to help everyone understand where that transmissibility is coming from. So if you look at it in an equation format, in the numerator you have the square root of 1 plus this term here, 2 times your damping times the ratio of your driving frequency F over your natural frequency F sub n in the denominator, and that term is squared, and that's all over the square root term where again you have 1 minus your ratio of the driving frequency over your natural frequency squared. That term is squared plus another term that gets squared, which is 2 times your damping ratio times your driving frequency in the numerator divided by your natural frequency in the denominator. So that is the equation. But to think of how it works, it's easier to think of it here if we look at this chart where you're looking at how damping affects transmissibility. So again, if we find a damping ratio of 0.50, which is the royal blue line here, we can see that that is really approaching a transmissibility of 1, which is the goal here for isolation efficiency. And again, when we have ratios that are 0.2, 0.1, 0.05, the magenta color, and the bright pink color, 0.01, you don't really have any damping whatsoever. So you're not close to the goal whatsoever with this transmissibility here, looking at this chart. So rather than dealing with transmissibility all the time, because I said we kind of, is kind of abstract or overwhelming if you're not familiar with the term, we like to talk in terms of isolation efficiency, which is basically if you take 1 minus your transmissibility times 100, that is your isolation efficiency. And we have it plotted in the next chart here. Okay, so you're looking at percentages on the vertical axes, 0 up to 100%, obviously. We have a red horizontal line at 90%, and that is signifying where you're starting, where you're getting an ideal amount of efficiency. If you've hit the goal of 90%, 91% isolation efficiency, then you're at a good point regarding trying to minimize and mitigate as much vibration as possible from that noise path in the building. And so when you look at your frequency ratio on the horizontal axis here, you're looking at that ratio of the driving frequency to the natural frequency. And to obtain an isolation efficiency curve, which is what we call this blue line, where it crosses the isolation efficiency of 90%, you're looking at almost a frequency ratio of 3.5. So oftentimes you'll hear the rule of thumb that you have to get your driving or disturbing frequency to be almost 3.5 times away from your natural frequency. Now, as we look at this isolation efficiency curve, the blue line, you can see that, okay, so yes, ideally you want to approach that 3.5 mark. But at 3, you're well above 85% isolation efficiency. So you have quite a bit of isolation efficiency at that point. And even 2.5 has you at 80% isolation efficiency. But you can also see that as you get closer to 2, 1.5, and then obviously less than 1.5, you're, decreasing your isolation efficiency significantly, and you're really losing that isolation efficiency as your driving frequency approaches your natural frequency. And when you have that driving frequency approaching the natural frequency, that's when you can get that characteristic of resonance. And I'm sure the structural engineers, civil engineers, even the mechanicals on the line may be familiar with. We call it, the nickname is the Galloping Gertie, but I think it's the Tacoma Narrows Bridge. The black and white videos that were popular at university, you would see the suspension bridge, and as the driving frequency approached the natural frequency of the bridge, it just started amplifying that behavior, that vibration behavior. And you could see that bridge waving up and down till it, basically started shaking itself apart. And that, is resonance. And again, that occurred because the driving or disturbing frequency of the vehicles were matching, the natural frequency of the bridge. So you had that frequency ratio approaching 1, which was very incorrect in a bridge situation there.
Angela, if you don't mind me jumping in.
Yes, of
a
course.
question came. Can you go back to your damping slide? Just
Yes.
maybe 1 or 2 back. Yeah, it doesn't really. That's fine. Just to show. A question came through regarding choosing damping coefficients with products. So in case more than one person had the same kind of question or concern, in general, that would be covered more in an advanced discussion of vibration isolation. But for our industry, HVAC predominantly, and power generation that uses mostly spring isolation, we just assume to have 0 or near 0 damping, and we move on with that selection rather than trying to design a damped system which would have both spring and dash pots within it. But hopefully that answers your question in a basic vibration isolation webinar. All right, you can go back.
Thank you, John. Thank you very much. Okay, so we've kind of discussed this isolation efficiency curve pretty thoroughly here. So really, how much isolation is required? So the ASHRAE Handbook Fundamentals Chapter 8 states that for most normal isolation applications in HVAC, that the isolation efficiency must be at least 90%. So in order for this to happen, ASHRAE recommends that we're greater than or equal to 3.5 for our driving or disturbing frequency in the numerator compared to the natural frequency in the denominator. So really that goal where subjectively people in the building are not going to be, vibration can be very subjective. You'll have some customers who are very sensitive to the feelings of vibrations. You'll have some customers who are very sensitive to any sound that's created from the structure-borne noise of vibration. But again, if you get up at that 90% mark, you should, meet the subjective goals of the people in that building, using that building. If you're a little bit less, if you're 85, 88%, you're going to meet, most of those people. But again, the goal should be to try to get as close to that 90% isolation efficiency from the ASHRAE handbook as possible. So here, looking at isolation efficiency at various revolutions per minute RPM, as John described in previous slides in his bullet points. So and I have to make sure that I look at this correctly because we have 2 shades of blue. The 550 RPM revolutions per minute in kind of a lighter, slightly light blue color is to the inside of this chart. So it's to the inside of the red, which is at 875 revolutions per minute. The green, that's at 1,350 revolutions per minute. And then the dark blue again, which is at 1,750 revolutions per minute. So as John was illustrating earlier, that it is an indirect proportion. You know, if you're looking at a static deflection of 2 inches with the 550 revolutions per minute, you're going to have, you know, almost, you're going to be at 93, 94% isolation efficiency. But you'll obtain that same 93, 94% isolation efficiency if we look at the green at the 1,350 revolutions per minute, with now you probably would have a static deflection of, you know, less than half an inch, probably around a quarter of an inch or so. So again, it's an indirect proportion, but it's good to know what the isolation efficiency looks at for various RPM, various revolutions per minute. So if we think about deflection, we want to kind of think about, you know, you have nominal deflection is one thing, actual deflection is another thing. You know, John illustrated before looking at that deflection as being the difference between that free height or that unloaded height, and then you had the material that was loaded on the right-hand side of his slide. And that deflection is what, you know, our goal is, and we need to think about that. But oftentimes in specifications, if they're not too specific, they'll list deflection, which is nominal or approximate. But what you actually have in the operating conditions out in the field is your actual deflection. So when you're working, you know, as a team, whether you're in the schematic or development design phase of the project, you know, the specifying engineers, engineers of records, the consultants, manufacturers, and, you know, even sometimes involving contractors, subcontractors, you know, we have to be on the same page, understanding the specification for a particular project. So again, looking at that static deflection, if you have your building structure here, and on the left you have your mass or your weight divided by your gravity, and your spring hasn't been loaded yet, that static deflection, once it's loaded, is shown then on the right. So it's that static deflection. And again, as John mentioned earlier, it is confusing once you get into spring isolators, especially spring isolators in our industry have an opportunity to have a preload at some point in time. But just because you're talking a 4-inch deflection spring or a 2-inch deflection spring does not necessarily mean that that spring is going to, you know, deflect that amount after it's already loaded. So we get into terms like differential deflection, and that's the deflection that you're going to see after the isolator is loaded. So looking at just the static deflection, just from the weight itself, you can look at it in all kinds of terms. You often see it expressed in the natural frequency here equals 1 over 2 pi in your denominator times the square root of gravity over your static deflection, x of s, where that static deflection again equals your weight in the numerator divided by your spring constant in the denominator. So you can look at it in those terms. If you set gravity in English US customary imperial units to 386.4 inches per second squared, you can look at it in the units in the second equation here. Oftentimes that is used as well with consultants, 3.13 times the square root of 1 over your deflection. And then finally, from my university days, I tend to think of gravity as 9.82 meters per second squared, but of course that is also 9,814 millimeters per second squared. You can think of it in terms of that gravity if you wish to, with 15.77 times the square root of 1 over your static deflection. So I hope that this is giving you some definitions, some ideas of how we look at Vibration, isolation efficiency, the transmissibility, a little bit about the damping, although John is very correct that typically in our industry, we can't count on damping. So unless it's specifically designed, we presume that that damping ratio is 0. Let's see. So at this point in time, I'm going to turn it back over to John, and he is going to give you some good ideas of things, what not to do, and hopefully do.
Okay, hopefully everybody sees the best practices, do's and don'ts screen. But before I move on, I wanted to address 1 or 2 questions that were popping up as you were going through, Angela. And you ended up on a good slide there because I guess we kind of, I want to say ignorantly or arrogantly assumed everyone understood we were using imperial inches pound second. And yes, so most of the time when we're discussing weight, we are talking pounds force, not pounds mass. Obviously, when Angela had a few equations up there, she threw in G. Hopefully that answered the question, but I want to address it for those who weren't looking. When we're talking weight, we're assuming pounds. And then somebody brought up a question about Chapter 48 in ASHRAE. It's worth repeating rather than answering it independently. The question was whether or not that's overly conservative, their assumptions in Chapter 48. And I actually look at conservative as a subjective term. And I made sure I highlighted and stressed that the members of ASHRAE 48 have many years of experience. So maybe analytically, something may show as a little overly conservative, but it comes from practical experience, knowing what to do, what not to do. So you may wonder why something is requesting 3.5 inches of deflection when analytically it doesn't show so, but I put my faith in the experience of those engineers to say there's a reason, that they've had issues, they've seen, and they understand. But if you really would like the answers whether the charts in Chapter 48 are overly conservative, I'd send ASHRAE TC 2.6 that question and see the answer that comes back. But also, before I move forward, I'm going to jump back to this slide again and Angela's discussion of nominal and actual. In general, the members of VISCMA, when we're selecting isolation, spring isolation predominantly in this chart for equipment, we're going to be up into the 95 to 100% range. Obviously, as I said, these are all asymptotic to 100%. You can never get there. But in general, so these first two, the green and the other blue, the 1350 and 1750, for this piece of equipment, we'd be selecting a nominal 1-inch deflection. Nominal being if the spring has a stiffness of 1,000 pounds per inch and I'm rating it at 1,000 pounds to have a 1-inch deflection. Actual is what's going to happen when the piece of equipment goes on top of it. I can't force 1,000 pounds onto my spring, and you never want to overload your spring. So in general, in actual installation, I may only have 800 pounds on that spring. So my actual deflection is 0.8, where my nominal is 1. But if you look at this chart here, moving from a 1-inch to a 0.8-inch deflection, there is no sensitivity or hardly any sensitivity on the isolation efficiency. So anything plus or minus a good 25% within this range where it would be selected, I'm not going to see a change in my isolation efficiency. So don't be worried that you're not getting a 1-inch deflection from a 1-inch deflection spring. Springs can only be made by wire diameter and heights and all the other geometry, so I can't have an infinite variety or an infinitely variable spring. I have a spring that's 800 pounds per inch, 1,000 pounds per inch, 1,200 pounds per inch, whatever it may be. So you have incremental selections. So you can never hit that 1%. And especially if I have a piece of equipment with 4 springs underneath it, it's impossible to balance that equipment so that each spring is at its rated load. So you'll typically get minus, you don't want to go plus because you're overloading the spring over its rated load, but you can be within 25% on the downside and not have any significant or any perceptible change in isolation efficiency. These other ones, at the lower RPMs, we'd be selecting a 3 or a 4-inch deflection spring at 550 RPMs, and it has the same issue. Within a range, there is no sensitivity to the isolation efficiency. Obviously, if you're selecting it down here, first of all, you're selecting it improperly. But now, yes, minus 20%, I dropped 10% in my isolation efficiency. Not a good thing. So all the selections that the manufacturers of Viscma will be making up in this range of the curves, such that any minor change from nominal to actual will not affect your isolation efficiency. It's an important point to remember when you're looking for problems, trying to find problems, or just reviewing an installation submittal. All right, so now I'm going to get into some quick slides on what to do, what not to do, what we typically see as an association in the field that happens. And the biggest issue we see is non-adjusted isolators. Most problem phone calls we get from installing contractors about, hey, I have a problem with this installation, or users of a building, it's the isolators are not adjusted. So our first answer to all of those questions is please take a picture and send us a picture of the installation. And it is extremely important, whether you're an engineer, whether you're specifying mechanical, or you're the installing contractor, I don't know who's on the call, but please make sure the installer reads all the instructions. Every manufacturer has slightly different variations. You can't say, well, I've been installing manufacturers A isolators, I know how to do manufacturers B. It doesn't work so simply. Read the instructions, and a large portion of your problems will go away. And the next biggest issue we see are the rigid utility connections. Piping, ductwork, conduit to the equipment. I can't stress enough how, especially on pumps, flex connectors must be on there. Something has to be flexibly connected. If you're rigidly attached to the next series in the system, and that next series is non-isolated, you have a rigid path for your vibration to go through, and it doesn't matter how many inches deflection you have underneath your pump, say, you're moving that vibration downstream. So the flexible connectors on everything, especially conduit coming up from the slab underneath, going into your equipment that's running the electrical wire or a gas line, they have to be flexibly connected. You're just going to completely short circuit the isolation. And as I mentioned, we always ask for pictures. Once the pictures are taken, we typically see it. And I'll repeat again on this slide, don't be concerned with the actual versus nominal. The isolation efficiency is not sensitive, and it's impossible to adjust the isolators to get the calculated static loads. If you think about any system installed on 4 springs, in any free body diagram, that is effectively an indeterminate reaction system. I can adjust those springs and have an infinite number of reaction combinations. If they're all adjusted roughly equally per the instructions, you'll get roughly the load that was estimated. But depending on the installing contractor and how they're adjusted, you can have 3 of the springs carrying most of the load, and I still have a balanced free body diagram. So it's virtually impossible to get all the isolators adjusted the way it was estimated. And one other thing on here that I don't know if I put before I move on is Angela touched upon the internal isolation. Some of the bigger pieces of equipment have internal fans that are isolated. If you're putting an isolator on the outside of that equipment, you'll need to lock out or put the blocking back in for the internal piece of equipment. Otherwise, you have a spring on a spring and you run into other issues. That happens very often. Rooftop units will have springs underneath the internal fans, but if you're putting them on a 2 or 3 inch deflection curb, that internal fan needs to be locked out. Another issue we see, and I'll show it on further pictures, but you may have seen it or heard of them, there's shipping spacers. The isolators, the housed isolators are typically shipped locked out with shipping spacers, such that the free height of the isolator doesn't change after you install it and adjust it, so all your piping and your plumbing into the equipment doesn't need to move. But you need to remove the spacers since they're short-circuiting your isolation. And every manufacturer has their own installation instructions. But most importantly is you should never remove any of the spacers until you can remove all of the spacers. As you're adjusting one corner of a piece of equipment, you're transferring weight back to the other corner. So if you've removed those spacers, you're going to bottom out the opposite corner of the equipment. It's no different if anybody's familiar with cars and watching NASCAR and they're turning screws on one corner of the car, they're moving weight to another corner. It's very similar on a piece of equipment adjusting isolators. So you need to keep the shipping spacers in there until you can remove them all, and then you'll level out the equipment and you won't short circuit. Another issue you have to always concern yourself with is point support. Now, I have a picture later on to describe it, but in general, some equipment is not designed to have a spring or some isolator point at its base at a discrete point. It needs distributed loading so it doesn't buckle, doesn't collapse. And it's the manufacturer of the equipment who determines that. And many of them will, those that require continuous support will send out some submittal cut showing this. You need to look for it, and if the manufacturer says so, you need to follow his instructions. If it wasn't designed for point support, you will have structural issues with the equipment after installation. And the next here is make sure the engineers selecting your isolation system have all of the necessary information up front. I read that because it's important. Without the weight of the equipment, the CG, the number of support points, RPNs, and such, we can't do our job and select the right isolation system. Once we start guessing or making assumptions, you know what happens. And so having all of that information up front, getting it from the manufacturer and everyone else is important to make the right selection. Because the biggest problem we would run into is less the weight. Most everybody has their weight. It's the CG, or center of gravity. Some equipment is heavily loaded on one end relative to the other, and I may need 2,000-pound springs on one corner or one end and only 1,000 pounds on the other. Without the actual CG, someone may guess equal distribution, and you're going to bottom out some springs, and you won't have any isolation. So it's important to get all of this information down. All right, now I'm going to jump and grab a question. What is the role of a concrete housekeeping pad in a vibration isolation system? The pad has no effect on the isolation system. It's more of a means of keeping, as it says, housekeeping. It's a means of the equipment to raise it off of the floor slightly for if there's any water intrusion in the building or for debris from going underneath, but it has no impact on the vibration isolation system. It may have an impact on the seismic, but right now that's beyond the scope of here. And somebody asked about specifications for flexible connections. That is also outside of the scope here. That you would go to a flexible connector manufacturer, and I believe they may even have their own association. But that's outside of the scope of what we're doing here. Let me go back to my slides. All right, so here's some field issues. I got a few pages of showing some field issues we run into. As I had mentioned before, you don't remove any spacers until you can remove all of them. This is an issue where the spacer was moved and the other isolator was adjusted, and you can see the top plate of this isolator touching the lower housing. The spring hasn't been adjusted and nothing's happening, so you do not have vibration isolation. But coincidentally on this one also, there was an issue with the support structure underneath, and it was improperly spaced, and that's why I mentioned it's very important to get all of the dimensional information for the equipment before you lay down your support structure. And the contractor had to add a separate piece of steel, in this case a channel, to support the isolator. That channel, if not sized right, can also become a spring. and can deflect under load, and that will destroy your isolation system. So other than this picture showing the top plate touching, it's showing a misaligned support structure. All right, now I'll repeat. Do not point support equipment that is not designed for it. So here we had a case where the manufacturer said no to point support. The contractor said yes to point support. Guess who lost? So in this case, that equipment required a structural frame underneath it to distribute the load coming in at the point. By the point, it means where the vibration isolation system is, in this case, a two-spring housing. And so if you look at this picture, another engineer did a great job for doing a well-designed frame underneath, put diagonal bracing, but it was ruined when the equipment was not properly supported underneath, and somebody went with the point support. And here, for outdoor applications, wind and seismic applications, you have to anchor the isolator to the building or weld it to building structure to be restrained. In this case, trying to use roof tar as a structural adhesive and shear does not work. And if you look closely, you'll also see this top plate also is touching the lower housing, so this was not adjusted properly. So we'd get this picture to the manufacturer. The pictures will tell us everything if you're having a vibration problem. And the vibration problem here is the spacer is removed, and it looked like there's a bent bolt, so the contractor tried to do something. I would have no idea what he tried to do. But more importantly, for an outdoor application, the isolator, it's going to come with holes in its plate to bolt down to the building, so when the wind blows, the isolator keeps the equipment, the restrained isolator keeps the equipment in place. And that is the last one. So now I'm just going to double check if we have another question. Like when you look at the minimum deflections. All right, so the question is dealing more with Chapter 48, and right now at this point, I think it's outside the scope of where we're going. Some of these questions are more directed towards ASHRAE. So Jody, I think at this point I'll transfer back to you. I'll just scroll back up to the beginning, and you can take it from here.
Awesome. Great. Thanks, John. So on behalf of VISMA, I want to thank Angela and John for presenting today, and for, of course, all of the attendees and participants on today's webinar. If you have any follow-up questions or requests for the VISMA office, I would encourage you to send an email to info@visma.com. For more information on the Vibration Isolation and Seismic Control Manufacturers Association, go ahead and visit www.visma.com, or we can also be found on LinkedIn. And on behalf of the association, I want to thank everyone again for joining us today, and I wish you all a great rest of your day. And that concludes today's webinar.